All right, grade 10 physics, brand new unit, second week of our online learning. And here we go. I decided to make some videos to help you along with your physics classroom reading and notes. And this is just to get us thinking about some of the big ideas in the chapter that we're doing right now. So the first big idea that we're looking at is static electricity. There, I stopped these kids from bouncing their heads and you can see their hair. The hair isn't flying around due to the wind. Every time they're leaving their head from the back of the sofa, their hair is starting to separate due to static electricity. And if I let it go, you'll watch. Every time their head touches the sofa, the hair comes down. And when they leave, the hair pops up again. Okay, that's because they're picking up static electricity as they're moving their body across these comforters. And their hair is starting to repel because each strand of hair is getting charged. All right, you guys understand that, you know that already, but I'm going to treat it as if we haven't ever learned that yet. Okay, so the first big idea is how can we harness our knowledge of electrostatic forces to do something that's pretty cool. All right, so last week I wanted you guys to research some magic tricks using electrostatic forces, because there's a lot of them. And you're gonna see in this presentation, that was where everyone got interested in electricity to begin with. They thought, hey, I can do some pretty cool stuff. I can move things at a distance. I can trick people and take their money. So a lot of scientists were fascinated by the magic of electricity. And then after playing with that magic and being fascinated exploring all these different devices that they're creating to capture electric fluid or electric charge, they started to develop technologies such as batteries, currents, circuits, sparks, okay? And then eventually they were able to make a link between electricity and magnetism and do some really cool stuff, and then eventually develop technologies such as Wi-Fi and radio. Okay, we even use electricity for things like levitation, and especially we know movement in the electric car that Jad made. All right, this example here is like a really high tech of electricity that you would learn in higher level physics next year. It's called electromagnetic induction, where we can use electricity to heat objects and levitate them. So take a look at that metal block in the middle. It's being levitated and heated and melted due to the principle of electromagnetic induction. We probably aren't going to touch that in this course, but if you're interested in taking a look at how that happens, definitely take a look at electromagnetic induction. It's something that we can be thankful for Nikola Tesla for. All right? All right, now as we move on, to begin our studies, we need to figure out what are electric forces. If I want to figure out what are the cool things that we can do with electrostatic forces, I need to understand what electric forces are, okay? So electric forces, first of all, electric forces are a type of force called a field force, okay? They're a force that don't require any contact. That's what's cool about it. Gravity and electric forces happen over distances. They're invisible. Okay, and that's why people associate magic with electric forces. So in all, they're forces that relate to charged objects. So if I put charge onto an object, it'll immediately have electric forces. And the forces act through space. Okay, they don't require any contact at all. So just as a visualization here, I stuck this video in here of using the force to move a cat through a distance. You can imagine the hand here is positively charged and the cat is positively charged, causing repulsion. Instant repulsion. All right. Okay. Now, because of that, at the early stages, what I wanted to present a little bit is where we discovered electricity. They had no idea about things such as protons, electrons. They didn't even know about positive or negative charge. But what they did know is that if you rubbed a piece of wood or something that is not metal with fur, okay, and you rubbed it with fur enough, it would start picking stuff up off the ground, okay, like loose pieces of paper. And so people thought that was magic. People thought that you're transferring some essential fluid of life by rubbing fur onto a stick. The life is being transferred, some type of force is being transported to it, some type of electric force, because we thought that electricity is related to life. If you read Frankenstein, you would understand that as well. That was part of this whole era of discovery of the magic of electricity. They thought that putting electricity or charge into somebody transfers life. So by rubbing the fur of a dead animal on a stick, all of a sudden you've transferred some type of life force or electric force into the object. And that force was able to pick things up. They didn't know why, but that was pretty cool. And so scientists who explored and didn't believe in magic, they started to understand some natural laws and be able to design some pretty cool experiments and make money from it. A lot of scientists didn't get money from the government, so what they had to do is put on these fancy science shows at balls, and some fancy aristocrats would hire them to do some magic tricks. And eventually we'll get to some of the electrocution magic tricks that kind of went bad a little bit later on. Now, before this time in the 1800s, 1700s, well back to the Greek times, they knew that a substance called amber, if you rubbed amber with fur, it really gets charged to the point where it can really spark. Okay, so they thought that amber was a magical substance that can store life energy or some type of serious energy, that can create sparks and pick things up. Like if you create static charge on an insulator, you can feel like a fuzz around it. So you can imagine what these ancient Greeks thought. They thought must be some type of magic stone. So it's a revered stone. And even today, that stone is worth a lot of money. All right, so people like it as a gemstone, amber. Okay, so in order to charge it up, you'd have to rub it with that little silk cloth over there or fur over time, and then it'll start to do things like this, pick up paper. All right, so here's an example. So in order to charge it up, you had to rub it. So how does that work? Well, as I discussed earlier, okay, everything has a cloud of electrons around it. And when you bring objects together and rub it, you're going to create friction. And friction is a result of electron clouds repelling. We talked about that when we discovered friction and calculated friction coefficients and things like that. So if I bring amber and cloth together and I rub them, the friction is going to cause the electron clouds to move. And for some reason, the electrons, due to that movement, will get excited and hop into the amber, causing the amber to become charged. And if I take a look at this, I'll see that the amber is a net negative charge. The electrons are hopped onto it. And then the cloth becomes positively charged. If I'd let them go, you'd see the cloth stick to the amber. And eventually they would fall off because the charge would hop back. Okay, the more we rub, the more work we're going to do with friction, the more electrons are going to go to that amber, the more charged it's going to become. Okay, but at that time in the 1800s and even for the ancient Greeks, they had no idea what charge was. They thought this was a fluid. All right, so but they did know that if you rubbed fur on amber, it becomes a certain type of electric force, a certain type of charge. Okay, likewise, if you took silk and rubbed glass with it, okay, it's also going to develop charge, but it doesn't develop the same charge. Amber develops a negative charge, and glass will develop a positive charge. So if you rub glass with silk, electrons from the glass rod are going to hop to the silk, creating a positive charge. So I wonder what would happen if I took that glass rod and that amber and I put them close together. I bet you they would attract or would they repel? Well, exactly, they would attract. Okay, so what they would find is if I brought amber and if I hung this rod from a ceiling and I brought the amber close to it, okay, the rod is going to start to move towards the amber. Okay, so if I drew this out, okay, we hang that glass rod, which is positively charged. And this is exactly what they would do. And then you take amber that is negatively charged. If you bring it close to each other, you would find that that glass rod is going to start to turn towards it. That's called attraction. Okay? On the other hand, if you brought another glass rod, it would repel, and it would start to move away with this magic force that would move away. And you can imagine that at the time in the 1700s and 1800s, this movement over a distance, nothing is touching and then things are moving, they would think that that's some type of magic. All right? All right, so how did we discover the nature of charge? Okay, well, I just kind of described this experiment, and that's exactly what's happening over here. So we discovered the nature of charge, that this is positively charged, and that's negatively charged. In fact, what a lucky guess. If they called that positive, it's a lucky guess, because they had no idea at that time what charge was. All they knew was that amber and glass attract, so they must be opposite in nature. That's what they would have said, that the nature of that charge would be opposite. That's why it's attracting. Okay, and later on in life, we figured out that they were absolutely right, which is pretty amazing. So in order to discover the nature of charge, what you can do, like in this demonstration here for electrostatic repulsion, is I can touch this insulator, which is plastic. Why I'm saying insulator versus conductor, okay, that's something that you're going to have to define in your notes. But an insulator stores charge. It can't move, the charge doesn't move around in it. So if I touch that object with a glass rod, or if I touch it with amber, charge is going to be transferred to it, it's going to be stuck on it. Okay, so I can take that plastic here, that half plastic heart, and I can charge it with negative charge, and then I can touch this with the glass rod, all right, and make that positively charged because electrons are going to hop from that into the glass rod. and then I can do some interesting experiments. Okay, so we can discover the nature of charge by observing repulsion or observing attraction. Okay, and so that's what they did. All right, and so they played around with this hanging glass rod or hanging amber, and they did many different experiments to be able to determine if you rub this object with it, what does it become? Does it become like glass? Does it become like amber? And you'll read a lot about that. Okay, so later on, and this is, I kind of skipped a whole variety of steps in the historical timeline, but later on they discovered that charge is not a fluid, it's not magic. Charge is a result of charged particles in atoms, and that was discovered actually close to the 1900s, pretty later on in that time scale. Okay, so if we draw, like Mr. Sickles taught you guys, an atom. Okay, here's my positive core nucleus, and I have an electron in some type of orbit inside of the atom. Okay, the electron is orbiting, or it's circling that proton, which you'll find out in higher level physics next year is totally wrong. Okay, but it's a fuzz of electrons around it. The proton in the nucleus is not able to move. So actually the character that is causing charge is the movement of the electrons. If I can pull an electron out of an atom, I would leave the atom with a naked positive charge, and now that material would have a positive charge. Okay, and if I pulled that electron off and I put it onto a glass rod, okay, now that glass rod would become negatively charged. Okay, so the character of charged particles that causes things to become charged is actually the movement of the electrons. Whether I pull an electron out or I put an electron into something is how I create charge. And the actual charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. Coulombs is the unit of charge, which we're going to talk about in the next lecture. Okay, so coulombs is the unit of charge, and the elementary charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. Protons are positive 1.6 times 10 to the minus 19 coulombs. The only difference is the sign. Okay, and how they discovered that is an interesting story that we'd go into in grade 11, but if you want to take a look at that now, it's a pretty cool discovery through our discovery of what the atom even looks like. That's an atomic physics chapter. Okay. All right, so we understand that these are the fundamental charge particles, and their movement is what causes charge. So when we rub materials, we're actually moving electrons from one material to the other. We're either adding them in or pulling them out and creating charged materials. Okay, so the next topic that I want to talk about, or you're going to read about, is measuring charge and the law of conservation of charge. Okay, so what instruments do we have in the lab to be able to measure charge? One of the earliest instruments that we had is an electroscope. Okay, an electroscope is a pretty simple device where if you see these little tails over here, those are really thin pieces of gold, wafer thin, like really light. Okay, and if I take this rod away, those thin pieces of gold are gonna just fall flat. They're gonna fall flat on each other. Okay, and if I bring a positive charge towards this metal plate that's on the top, what's going to happen is electrons are going to be attracted to that positive charge, and they're all going to migrate up to the top and be attracted to that positive. As long as I don't touch it, they're all going to be attracted. So this surface at the top is going to have all the electrons hanging out, and if all the electrons move up that metal to this side, they're going to polarize the metal, and they're going to leave behind positive charges on the gold foil. Okay, and those positive charges are going to repel. Okay, the greater the charge of the object is that I'm putting, the further distance those leaves are gonna go apart. Okay, the greater the distance, the greater the charge. All right, and that's the original way of seeing how much did I charge this. If I rubbed that piece of that piece of glass with silk for, let's say, 1 minute, what's going to happen if I rubbed it for 2 minutes? Is it going to make the leaves go further if I rubbed it for 3 minutes? And they started to quantify charge based on how far these leaves went. Okay, and another tool, all right, another tool that we use to measure charge are called pith balls, all right? And pith balls look like this, and they're made of basically styrofoam, which is also a very light material, and it's an insulator, and it really likes to accept charge. Okay, so if I approach a pith ball and I transfer an electron onto it, and I transfer an electron onto the other, okay, they will start to repel. like you can see in these diagrams. I can charge each one separately and I can see how they're going to react, whether they attract each other or they repel. That's one way for me to determine what the nature of the charge is on an object if I touch either object, okay? And I can actually measure the force of repulsion, which is a challenge problem in one of your units. I don't want to tell you how to do it right now, we'll go over that, but I can measure the force of repulsion by looking at the angle that those pith balls move away from each other. The greater the angle, I will actually be, by using the force of gravity and the force of tension, I will be able to estimate the force of repulsion, which is a pretty cool experiment. So pith balls allow us to actually calculate the force of repulsion. And then later on, you'll find an equation. If I can calculate the force of repulsion, I can actually calculate the amount of charge that's put on those pith balls. Those are some challenging problems that you're going to face, okay? So this diagram over here shows when I charged up the pith balls, they're going to be attracted. When I charge them up with like charges, they're going to repel. Okay, these are the other two situations. Now something else that happens that's pretty interesting, if I just had one pith ball hanging, okay, it's hanging from a ceiling, and if I approach that pith ball with a positively charged glass rod, as I start to approach it, what do you think is going to happen? Do you think it's going to move away? Do you think it's going to be attracted? Okay, well, I'll explain why it actually becomes attracted. Even though I'm not touching it, this is a neutral, that's a neutral ball. Why would a neutral ball become attracted to a positively charged rod? Okay, that also explains why would paper in this diagram over here, why would paper be attracted to paper's neutral? Why is it being attracted to a charged rod? Well, the reason for that is because of a phenomenon called polarization, like I talked about in your notes. So polarization. So what'll happen as I approach that neutral ball with a positive charge, all the electrons in that material are going to start to migrate to this side. Okay, so that side of the pith ball is going to become negatively charged, leaving behind a positively charged surface on this side. So what happens is the pith ball becomes polarized. And as I get closer and closer, that pith ball is going to start to be attracted because it has a negative surface that's going to be attracted to the positive surface. That's what's called inductive charging, okay, or polarization. All right, so our last topic that I wanted to present here is charging by induction. We can charge by contact, okay, by touching the pith balls, and we can charge by induction. I'll go over the law of conservation of charge in the next talk when we do Coulomb's law. I think that's a better place to put that one, okay? So let's start by doing charging of induction. How can I make a pith ball, or how, not a pith ball, sorry, how can I make a metal ball, this is metal, okay, how can I make it positively charged? Okay, this is attached to the ground, or it's not attached to the ground, sorry, oops, okay, how can I turn that neutral metal, how can I turn this neutral metal into a positively charged metal? That's what we're after, okay? And I'll show you how I can do that by charging with induction. Okay, so if I have that neutral metal, okay, I'm just going to erase this. If I have that neutral metal and I start to approach it with a positively charged rod, okay, what's going to happen? Okay, and let's just say this is wood, okay, which is an insulator, and this is a metal charged, this is metal, okay. As I approach that metal ball with a positively charged rod, what's going to happen? Well, polarization is going to happen. You're going to have the negative charges of the electrons move to that side, and I'm going to have positive charges left on that side. In order to make that metal ball positively charged, there's a few things I can do. I can bring this positively charged object and I can touch that, make them contact, okay? And if I make them come in contact, these electrons are going to hop over here, okay? And then when I pull that rod away, I'm going to be leaving behind a positively charged metal ball. But that's not charging by induction. That would be charging by contact. And that's That's simple. We've already talked about that, charging by contact. Okay, so what I want to be able to do is charge that metal ball without any contact whatsoever. Okay, so I'm going to erase all this and start over. All right, so one way I can do that is what I want to do is I want to drive, well, I'll just draw that metal ball. I want to drive the electrons in that metal ball away. Okay, so instead of approaching it with a positively charged rod, I'm going to approach it with amber. Okay, so this is amber that is negatively charged. And as I approach it, the electrons want to get away, okay, leaving behind a positively charged surface. And if I can get those electrons to want to leave so much that they're going to go somewhere else, okay, I can do that by attaching that metal ball with a wire to the ground. Okay, this is the surface of the Earth. As I approach that metal ball with the amber, those electrons are going to go through the wire to the ground. And if I then cut that wire, okay, but before I remove the amber, the electrons will not be able to come back, and I'll end up making that ball positively charged. Okay, so that's charging by induction. Okay, there was no contact made. All I was doing was pushing charge by bringing a charged object closer in space. Okay, so we have charging by conduction and charging by induction, and those are things I just wanted to take this little note here just to talk about a few concepts that you're going to be reading in the physics classroom to answer your notes that you have to do this week in the note takers. All right, I hope this helped.